Today I'm going to be talking to you about how to draw a graph using a pencil, a ruler and a piece of paper. So the very first thing that we need to decide is what type of graph we're going to be using. So the two main types of graph that we draw in science are a column graph and a line graph. So general rule is that the column graph is where you've got category data and number data. So for example, if you were tallying up the number of certain coloured cars that pass by in a certain period of time, the colour of the cars will be the category data and the number of the cars, obviously that's number data. Earlier we did an experiment on heating water using a Bunsen burner over a period of 20 minutes and measuring the temperature every 2 minutes. And this would be an example of where we'd use a line graph, and the reason is that time is number data and the temperature of the water is also number data. So where we have number data, and that's continuous number data, versus number data, we will be drawing a line graph. Here is a table of data that we collected for this experiment earlier, and you can see that this table has two columns, one with time with the units minutes, and the second column we have temperature with the units degrees Celsius. We had a zero temperature, so before we started heating the water, where we took the temperature of that water and then we started heating and recording the temperature every 2 minutes. So this is our data from the experiment, and this is what we're going to be graphing today in a line graph. Again, number versus number, time and temperature, both number data, so it is appropriate for us to do a line graph. We start with a heading, and one that can describe what's going on in the experiment and the type of data that we're graphing, and it needs to be done well enough so if someone who wasn't there for the experiment, didn't know anything about it, came along, read that heading, they'd know what this is all about. And in this case I've used the exact same heading as for the table. Next we draw in our axes for the graph. So we have a horizontal axis, so the one at the bottom, often called an x-axis, and we have the one that goes up the side, the vertical axis, but that's often called the y-axis. So we always put the independent variable on the x-axis, the one at the bottom, and we put the dependent variable on the y-axis, the one up the side. So in this case, time is the independent variable because it works independently of our temperature. Time proceeds independently of what the temperature is. The temperature is going to depend on the time. So as time passes, the temperature is going to be different. So in this case, dependent variable is the temperature. It's going to go on the y-axis, the vertical one up the side, and time, being the independent variable, is going to be on the x-axis, the horizontal one, down the bottom. So next we draw in the scale for both the x-axis and the y-axis. And this is probably one of the trickiest parts of doing a line graph. And it's probably the one that takes the most practice and to get used to doing it. So you need to know two things for each axis. So the first thing you need to know is what the largest value is that you have for that variable. And the second thing you need to know is how much space that you've got on that axis to fit that largest value in. So in this case, we had 20 minutes of time, so 20 divisions, if you will, and we have space there, 21 squares across from our 0 to the edge of our graph on our line paper. So won't worry about the 21st one, we'll just go to 20, so that's nice and easy for us to work with. And we'll say that each square is 1 minute, and we recorded our data every 2 minutes. So on the x-axis there, I've marked in for every second minute a value for time. For the y-axis, we've got our top temperature, our top value being 100 degrees Celsius, so our greatest value is 100, and counting the squares up from the 0 to the top of the y-axis, there's 25 squares. So I could have just simply said 100 divided by 25 is 4, and made each of those little squares up the side on the x-axis worth 4 each. But I decided to make it a little bit easier for myself. I just wanted to have each square as 5, and just makes it a little bit easier for me to put in my data later on. Either way is fine, but generally we do try to fill up the space as much as possible. So in this case, I've got each square at 5 degrees Celsius, well, has a value of 5 degrees Celsius. Another trap that some people do fall into is they just look at their table and they just take the values for the temperature and just write those up the side equally. And that is not going to be a consistent scale, and you're not going to get a representation of your data there. And you always get a straight line in that case, and that might sound good, but it's not a representation of how the rate of change really occurred in the experiment. At this point, we can start entering our data values in on our graph, and we do that by looking at our table that we recorded the data from in the experiment in the first place. And for each time value, we go to the temperature value moving up the graph, and we put a small X, and the center of the X indicates the data point. So for the first one, we had at 0, so before the 0 minutes, before the experiment started, we had 22 degrees Celsius. So we go to 0 minutes on our x-axis at the bottom, and we go up 22 degrees and put a small X. And we do that for each of the other data points until we've got one right from 0 through to 20 minutes. And you can see there in the picture that I've taken of the graph I did earlier that we have a bunch of X's that we can then go and join together. There are two ways that we can join these data points together on a line graph. So the first would be a line of best fit, and this is appropriate when we know we're going to have a linear relationship between the two variables. So what that means is that as one goes up, the rate of change for the other is constant. So something like Ohm's law for electricity, for example, is an example of a linear relationship. So as voltage increases, the amount of current will increase at the same rate as the voltage increases, resulting in a straight line. But of course, when you do measure these things, your measurement is not perfect, and you're going to have data points that will be slightly off a perfectly straight line. So you would draw a straight line using a ruler that is a best fit, an average of those data points. However, that is not at all appropriate for the experiment that we have. This is not a linear relationship, and it's very clear, you can see with those where the data points are. So in this case, you would draw a freehand curve between the data points, making it as smooth as possible. And this is to help represent all of the data points that could have been taken in between our samples that we took every 2 minutes. So in this case, a freehand curve drawn in pencil between each of the data points. Looking at the table of data next to the graph of data side by side, you can see that looking at the graph, it's much easier to work out what's going on in the experiment as far as a relationship between the time and the temperature of the water. So we can see that although it started at 22 degrees Celsius, it increased rapidly once the heat of the Bunsen was applied, up to about 8 minutes before it started to, the rate of heat increasing started to taper off a little bit until it hit the 10th minute at 100 degrees, and then there was no change from 100 degrees for the rest of the time in the experiment. So what I did there is very brief analysis or interpretation of that graph. So in general, if a graph like this has a slope going upwards, that means that's an increase in the temperature. If there was one going downwards, that would mean a decrease in temperature. And when I say going downwards or going upwards, I'm going from the left to the right there on the x-axis. And where it's flat at the top, that indicates no change. So time's proceeding, but there's no change in the temperature. So a couple of things to note for line graphs there. So increase in temperature is where the slope is going upwards. A decrease in temperature is where the slope is going downwards, and no change is flat. And the steeper the slope going up, the greater the rate of change, or the greater the rate that it's increasing temperature, and the steeper that it's going down, the greater the drop in temperature. So over time. What we can also do with graphs is work out what's going on between points, and also work out maybe what's happened past our data points. So these have two special names. The first, where we try to work out what data points between points that we've already got, this is called interpolation. And where we try to work out what's going on beyond our data set, so beyond the 20 minutes in this case, that's called extrapolation. So if we talk about interpolation first, this is where we attempt to find the value of a data point that we didn't actually measure. So sounds complicated, but it's not. I'll give you an example in this particular experiment. We took temperature measurements every 2 minutes. So let's say I really wanted to know the temperature at 7 minutes, but we didn't measure that. I can use this line graph by finding the 7 minutes on the x-axis, and I follow it straight up until it hits the curve, and then I draw a line across to the y-axis, and in this case you can see that it would be 80 degrees. So I found that at 7 minutes the temperature of the water was approximately 80 degrees. I say approximately because this is not as accurate as the measurements that I made. As discussed earlier, my measurements aren't perfect either. There might be some small errors, but we can trust my measurements much more than an interpolated result. This would be reasonably accurate. It would be somewhere around the 80 degrees, so that's pretty good. However, if I wanted to work out what the temperature was after, say, 30 minutes, 40 minutes, I would be using a method called extrapolation. And that's, if I had room on this graph, I could do it. Obviously, I don't have much room left at all. But it's continuing on the trend line on the graph and attempting to work out or estimate what the value might be. So extrapolation is generally not very accurate at all. And in this case, it's probably not appropriate because we generally know it's going to be about 100 degrees after the 30 minutes anyway. But it's certainly, for certain activities, extrapolation is really, really important. So say taking census data, we take population trend over time. We measure time on the bottom and population up the y-axis, and we graph that over time up to present day. And if we can continue on that curve and project forward in years to come, we can get an estimate of what the population will be on a particular date into the future. Obviously, the further you go into the future, the less accurate you're going to get. And it's not as accurate as interpolation, that is getting data between measurements that you've made, and that is not as accurate as the actual measurements that you've made yourself. So 2 points there, interpolation and extrapolation. So both are getting data that you didn't measure from the graph, and interpolation, not as accurate as measuring it yourself, but it's not too bad for accuracy. But extrapolation, you lose a lot of accuracy doing that, but it still can be quite useful.